Well, now I want to introduce Earl Hackett. You remember Earl? Earl did a great segment for us, or several segments for us, really on CAD design and how to do CAD and this kind of thing. And he's back. He's going to build a house this time for us, I believe. So, Earl, welcome. So happy you're back.
Yeah, here I am. Okay, great. There's going to be there are going to be three parts to this. First one is tonight, and we're going to talk about design considerations based on the printer that you're using and the structure, the structure you're trying to build. Then the second part will be on component design and joining them together. And the third part will be on painting and finishing. And I ran into some problems there. I think I have some solutions that sort of surprised me. So let's get on with this one here. The model I'm building is the bunkhouse at Thurmond, West Virginia. This was where trainmen would stay overnight waiting for the next job, their next trip. It has, it's about, I'm going to guess about 80, I think it's about 80 feet, 90 feet long. Very basic construction, shiplap siding, tar paper roof. And it's interesting. Well, here's the drawing that I built it from. There are two sections. On the left side, you have a somewhat larger area. On the right side, you have a somewhat smaller area. And I was wondering, what the heck is this? Well, it turns out the enginemen and the conductors and the locomotive engineers, let's say the engineers and the firemen, stayed on the left side where they have more room, and the brakemen were confined over on the right-hand side. I don't know why that was, but that's the way they had it set up. And they had you can see you have an entrance there. You have a cooking area, some locker rooms, and it's on a slope. So it's actually, most of it's built on pilings, as is almost all the structures there in Thurmond. Well, this shows the building with the print volume that I have in my Saturn printer. It doesn't fit. So we're going to have to break that thing up into multiple parts. And we wound up with 6. We have 2 roof sections, 2 wall sections, and 2 foundation sections. Now, what I wound up with, the actual part actually has pilings coming down here to fit on my layout. But this is an earlier drawing, and I just never bothered making a print of the current one. But you'll see it. Okay. One of the limitations you have with the printer is the resolution. And the two printers I have are illegal. My first one was a little Mars 2P. It's a relatively small printer, and the Saturn is sort of a medium-sized printer. But the resolution is pretty darn good, 0.05 millimeters, or about 2/1000 of an inch in all 3 axes. HO scale 1 inch is about 0.3 millimeters, so you get 6 layers for every inch. It gives you a pretty good resolution of things like rivets and that sort of thing. Now, the resolution, though, is highly dependent on exposure time and orientations. You can find that here. This is what you call a resolution target, or whatever you want to call it. But here you have fins. These 3 here are 0.05 millimeters. A couple over here are 0.1, and then you get a 0.15. They go up to fairly heavy things. And you have the same thing over here on these angled fins. Over here, this section here has grooves for see what your clearances are between pieces. And this allows a picture, but I had nothing to focus on. This was a 3-second exposure, and I could not focus on anything. Everything was all rounded and fuzzy. But as you can see, the 0.05 millimeter pieces, they just didn't make it. The 0.1 millimeter pieces here look like they are there, but the edges are all rounded and they're pretty ugly. You go over here to the angle pieces, and I was able to get better focus on this. The 0.05 millimeters, they aren't even there. They're gone. And the 0.1 millimeter piece is pretty well shot as well. Now, one of the things you want to notice that all these, even where you have a good fin, for example, here, this channel is plugged up. And I'm going to get into why that happens later on. But here I've increased the exposure to 4 seconds. And the 0.05 millimeter fins are looking really good. I mean, that's a pretty doggone nice, sharp image. But the 10.1 millimeters, of course, they're there, but all these channels are all plugged. So you can resolve a fin or a standing of what do you call it, stand-up piece or a vertical, a solid piece, a lot better than you can resolve a hole. If you go over here, this angle, these pieces here, they were missing in the 3-second exposure. They're looking pretty good, but those 0.05s, they don't even show up. Just a couple little nubbins here. That's about all there is to it. And you notice that now these channels here are starting to plug up too. They're starting to fill in because of the longer exposure time. Okay, for the resolution, there's I've go back to 45 years ago now. Yeah, it was printed circuit boards, and some circuit board shops would actually go out and they wanted collimated light, so they get real good sharp exposures. They got a greenhouse. They hang the doggone parts up in the greenhouse and let the sun expose them. About 2-minute exposure to get it done. And there's problems with that. But then we went to parabolic reflectors using quartz or hydrogen vapor lines, all sorts of high intensity UV lights. Then we tried laser imaging. And they actually, this is getting into the time where we started to do some 3D printing. The Form Lab started with laser imaging. It's well aligned, but the exposure times are long. And I was not impressed with the resolution I saw from some of their samples. And finally, you come up with columizers, and you can get improved exposure time, but you lose some resolution. Now, here's the problem you're looking at. Let's say we just take an array of LEDs and you put them down here and you try to expose your layer of your polymer. The light's going out in all sorts of directions. And as you can see, these two here are out, and you would hope that you would have a slot in here that would be, this would be a liquid and you wash it away. Well, light comes from here and comes across, and you can see this gets truncated very quickly, and before long you don't have any opening there. So what Illigu has done, they put in columizers, and all these and these are small. I think they're about 1 centimeter across in square, and the LED, the LED diode is about 2 or 3 inches down from it. So then they have a LCD screen, and that's what actually forms the image. So where the LCD screen is transparent, the light comes up, but you can see even here, we're losing some. For this one here, it comes across, hits this, and you're losing some material. You're losing the opening here. And that's why the a freestanding part, a solid part, is a lot easier to expose than a channel. There's more to it. The chemistry gets complicated, and I'm not going to go into that. I'm a chemist. I worry about that kind of stuff. But at any rate, another problem you have with the liquid crystal LCD or liquid exposures, liquid materials, the parts are suspended upside down, and they grow from the exposure surface, and they're held on an aluminum plate with an array of columns. So all the columns all come down. This is the I printed this one from the with the roof pulling it up, because you're not going to be able to see the roof, so I don't care what that looks like. So this is the columns eventually will come down. All these orange areas are going to have something attached to them to pull them off of the ground, the plate as the part's being constructed. And that's what it looks like. Now, this is a program called Lychee Slicer. It's this is their free version, and I've come to dislike it. You have a lot of freedom in putting in the columns where supports where you want them, but if you turn it loose and just say do it automatically, the software is pretty bad. You can see you have large gaps between these areas here, and this is edge here. You're going to be able to see that from the side, and I just find the automatic part really a pain, and it takes forever to fill in the gaps where you think you need them. There's another slicer that comes with it's included free with the Elegoo printers, and it's called Chidubox. Where they get these names from, I don't know, but you can see they put the positions here along that edge are very close together, and so you get pretty good solid edge there. And when you from the side, you can't tell that there's these lumps in the place. And the surfaces, the flat surface here, very uniform positioning of support members. And this is what it looks like when you're printing it. Now, this is the build plate. It was printed upside down from this view, but this makes it easier to see what you're looking at. And as you can see, these come way up, and one of the problems is you can wind up putting a lot more material into these supports than actually is in your model. That gets expensive. So you want to think about how you're going to position this thing. That's why I printed from the bottom up. At least a lot of these supports are just short because you only have a few long ones coming up to the overhead. As good as as good as Chidubox is, it does some stupid things like this guy right here. You remove that before you print. You could go in and just click on it and delete, and it goes away. There's no need for it to be supporting here, and you're going to get a lump on the surface of your model. You're also going to have lumps up here in the overhead, the top here, and they could be a problem. And we'll get into that in a few minutes. You notice that if my window frames are also 3D printed, and I build the sashes for them separately. They go in as independent pieces so they can position partially opened or something like that. But one of the problems is you got to fit this is going to close up a little bit. And I turned out in my case, I didn't leave enough clearance here close up, and I had to go in with a little file and open them up a little bit. Now, when I talk about lumps, that's what they look like. These were the lumps on the first floor I built, for foundation I built, and you can see these things do stick up quite a bit. If you're going to make a joint on this surface, if this surface has to be attached to something, you're going to have to sand it down. So you want to position parts so that any joint, any surfaces are going to be joined together, do not require this kind of support. So these are the minimum dimensions I talk about for clearances. And this will turn out not to be enough. I left a 10.1 millimeter clearance in here, and this thing closed up. Now in this case, I had to go in and sand down those little lumps up here, but just taking those lumps off still didn't give me enough clearance in this opening here. So I had to go in and clean this up with a feather edge file. But down at 0.7, 0.6, something like that, top and bottom. If you have something that's going on tab that has to fit into a slot, open it up some more. So these are the problems you run into in designing a model. That's a very brief overview of how you're going to build things. Next week, I'm going to get into designing the parts themselves and the designing joints. Because one of the problems you saw that building was in two pieces. It's going to be put together. You don't want to be able to see a seam where where those two halves come together. So I'm going to go into how I go about hiding these seams where you can't see them.